We will now use the concept of electric field and the electric field intensity to solve problems. Alright, let's start with one. A charge of 40 microcoulomb is at the origin. What is the magnitude and direction of the electric field on the x-axis at x equal to 6 meter and b at x equal to negative 10 meter? Sketch the function E of x, electric field intensity as a function of x, versus x for both positive and negative values of x. Alright, first of all you need to visualize, got to draw a picture. And let me remind you, we did problems on calculations using Coulomb's law. And those who were not familiar with vector addition, finding the sum of two or more vectors by breaking them into their components. Now, I hope you have now some idea how to do that. We are going to use the same concept in this lesson again, because electric field is a vector quantity. If you want to find the resultant field intensity at a point, you should be able to add vectors due to several electric field vectors, and we will use the same method. Break each vector into components and then add them. Alright, this is a simple one. Let's do this one now. Since the field due to a positive charge is directed away from it, for positive x values the field will be positive, and for negative x values the field will be negative. Is that right? A charge of 40 microcoulomb is at the origin. So you have a charge of 40 microcoulomb placed at the origin. Here is the charge. Now the field to the right will be positive and the field to the left will be negative. I suppose that is not a difficult concept to understand, because the field lines due to a positive charge will all originate from it. The field lines will originate and go away. The field lines originate and go away. So on the right, the field lines are along the positive x-axis. On the left, they are along the negative x-axis. So if the field is positive on the right, the field is negative on the left. Now here is the charge at the origin, the 40 microcoulomb. We need to find the magnitude of the field at x equal to 6 meter. What is the equation we developed for the magnitude of the electric field intensity at a distance r from a charge q? You remember that one? E equal to kq over r squared. So you got E, this is the point at x equal to 6 meter. You got E equal to kq over r squared. K is 9 times 10 to the 9. Q is 40 microcoulomb, which means 40 times 10 to the negative 6. And R is 6 meter. So using that, we've got E equal to 10 to the power 4 Newton per coulomb. Now what is the direction of this field vector? This field vector will be directed away from the charge. Right, so this is 10 to the power 4 Newton per coulomb, directed in the positive x direction. The magnitude of the field at x equal to negative 10 will be again E equal to kq over r squared. The only difference there is now r is 10, r squared is 100, and that will be 3.6 times 10 to the 3 Newton per coulomb, and this is the point 10 centimeter to the left of the origin. And what will be the direction of the electric field there? The electric field at this point will be directed away from the origin. Now this field is in the negative x direction. Alright, now what is the next thing we need to find? Sketch the function Ex. What does Ex stands for? Electric field in the x direction. Remember, field is a vector quantity. It can be expressed as components, x component and y component. So Ex stands for the electric field in the x component. So you can see electric field in the x direction. The field will be very large as you come closer and closer to the charge. Field will be very large and positive, and as you go away the field reduces to 0. Is that right? I can actually draw that graph right here. So the field on the right will be like this. You see, as the point gets closer and closer, the intensity of the electric field will be very large. And as you start going away, the intensity becomes less, and it gets closer and closer to 0 asymptotically. How about on the left? On the left the field is negative, and at a point very close here, it will be a very large negative value. In other words, the field on the left will be like this. I'm going to draw with the blue line. Now that is the field on the left. You see that? So the field on the right, positive and decreasing, and the field on the right, negative and increasing. Well, what it means is it actually gets closer and closer to 0 on either side. Okay. The function that describes the field density is Ex equal to kq over x squared. That is the expression, and if you can draw a graph of that, and look at that here, I used Maprofile to produce the graph of this function. And this represents how the x component of the field intensity changes with the values of x. Okay. The function only describes how the magnitude of E changes along the x-axis. Well, actually not. It also tells you the direction, because on the right side it is positive, on the left side it is negative. Alright? At a point very close to the charge, the field is either positive infinity or negative infinity, very large. And at very large distances, as you go far away, you can see the field get closer and closer to 0. Let's try another problem. When a test charge Q0 equal to 2 nanocoulomb is placed at the origin, it experiences a force of 8 times 10 to the negative 4 Newton. What do you think is what do you think is the reason for that force? When this charge Q0 is placed at the origin, it experiences a force. Well, it experiences a force because there is an electric field at the origin. Right? Otherwise it will not experience a force. Now, part A, what is the electric field at the origin? In other words, what is the electric field at the origin which will exert this force on this charge? That is what we need to find. B, what would be the force on a charge of negative 4 nanocoulomb placed at the origin? If the force is due to a charge on the y-axis at y equal to 3 centimeter, what is the value of that charge? Well, I don't think you understood this question very well. But let me see if I can make it clearer as we go on. Well, here is the origin, and we have a charge Q0 equal to 2 nanocoulomb placed there, and we are told that it experiences this much of force. Well, that means there is an electric field there. it experiences a force of how much? 8 times 10 to the 4 Newton in the positive y direction. So this is the force experienced by this 2 nanocoulomb placed there. Now remember, this is a positive charge, is that right? Now tell me, if a positive charge is placed in an electric field, what will be the direction in which it experiences a force in relation to the direction of the electric field? Remember, the direction of the electric field is the direction in which a positive test charge would move. Well, that means if this 2 nanocoulomb experiences a force in the positive y direction, that means this is due to an electric field at the origin directed in the positive y direction. Alright? The magnitude of the field at the origin. Remember, the definition of electric field is force experienced by a unit test charge. A 2 nanocoulomb at the origin experiences this much force. Therefore, if you place a unit test charge at the origin, what will be the force? It will be the force divided by the charge. The force per unit charge is force divided by the charge. So E equal to F over Q0 will be the force per unit charge. The definition of the electric field is force per unit charge. So a charge 2 nanocoulomb experiences a force of 8 times 10 to the negative 4. Therefore, the electric field at the origin, which is responsible for that force, is force per unit charge. That is force divided by the charge. Convert the charge to coulomb. And that is 4 times 10 to the 5 Newton per coulomb J. So that electric field is in the positive y direction and its magnitude is 4 times 10 to the 5 Newton per coulomb. Now, if you place a negative 4 nanocoulomb at the origin, in place of, you remove this 2 nanocoulomb and place a negative 4 nanocoulomb at the origin, what will be the force that will experience? Well, F equal to E times Q, is that right? Force experienced by a charge is E is the force per unit charge multiplied by the charge. So force experienced by a charge will be E multiplied by Q. E is this, that is 4 times 10 to the 5 times negative 4 times 10 to the negative 9, and that is negative 1.6 times 10 to the negative 3 Newton J. So a negative charge, now if I have an electric field directed this way, a positive charge will move in the direction of the electric field. A negative charge will move opposite to the direction of the electric field. So if a positive charge experiences an upward force, a negative charge will experience a downward force. I hope that is clear. So if you now place a charge of 4 nanocoulomb here, it will experience a force 4 nanocoulomb. It will be the electric field multiplied by 4 nanocoulomb. That is 1.6 times 10 to the negative 3 Newton in the negative y direction. Right. So we have now removed the 2 nanocoulomb and also the 4 nanocoulomb. But you know there is an electric field existing at the origin. Is that right? We don't know who causes that field. The C part, we want to find out what causes that field. If the force due to the, what I mean is, when I say if the force on that original 2 nanocoulomb is due to a charge placed on the y-axis at y equal to 3, somewhere here. That's right. You see that original electric field of E equal to 10 to the power 5 in the positive y direction. We are now told that it is caused by a charge Q placed at y equal to 3. Now, we need to find what is the value of that charge. In other words, what electric charge placed at y equal to 3 produces at the origin an electric field E equal to 4 times 10 to the 5 Newton per Coulomb. That is what we want to answer. You know that E equal to KQ over R squared, where this Q we need to find. What is this R? R is 3, and E we know the electric field at the origin. So E is 4 times 10 to the 5 Newton per Coulomb. R is 3 meter. K we know, therefore we can find the Q. So let's put the values in there. K is 9 times 10 to the 9 times Q divided by R squared is 0.03 all squared, and this quantity equal to E, which is 4 times 10 to the 5 Newton per Coulomb. And now you can solve for Q. Q equal to, look at this, E R squared divided by K. And now this is the E value, the electric field at the origin. R is this, R squared is 0.03 squared, and K we know. So that will be R squared times E divided by K, and that will be 4 times 10 to the negative 8 Coulomb. So the electric field of 4 times 10 to the 5 Newton per Coulomb at the origin was actually produced by a charge of Q equal to 4 times 10 to the negative 8 Coulomb. Can you write this using nanocoulomb? How many nanocoulombs is this? 4 times 10 to the negative 8 coulombs is 40 nanocoulomb. Is that right? Yes, that's equal to 40 nanocoulomb. Okay? I hope you understood the concept of the problem. Let's do another one. Two equal positive charges of magnitude Q1 equal to Q2 equal to 6 nanocoulomb are on the y-axis at y1 equal to positive 3 centimeter and y2 equal to negative 3 centimeter. What is the magnitude and direction of the electric field at x equal to 4 centimeter? B. What is the force exerted on a third charge Q0 equal to 2 nanocoulomb when it is placed at x equal to 4 centimeter? Well, that's simple enough, I think. Well, this is the situation. You have a charge Q1 equal to 6 nanocoulomb at y equal to 3. You got another charge Q2 equal to 6 nanocoulomb at y equal to negative 3. And these are centimeters. So you need to convert them to meters. Well, you need to find the electric field at a point x equal to 4 at this point. Alright. First of all, we need to figure out this distance, the distance of charge 1 from this point. You see, if this is 3 centimeter and if this is 4 centimeter, this will be 5 centimeter. Is that right? 3, 4, 5 are Pythagorean triples. So this distance is 5 centimeter, which is 0.05 meter. Well, if this is 0.05 meter, this also is 0.05 meter. So we now know the distances of the two charges from that point. Okay. Field at x equal to 4 centimeter due to charge Q1 will be, what's the equation for field at a point due to a charge? Is KQ over R squared. E1 equal to KQ1 over R squared, where K we know, Q1 is 6 nanocoulombs, 6 times 10 to the negative 9, and R squared is 0.05 squared. There you are. KQ1 over R squared, and calculate that. Always keep a calculator with you when you listen to the lecture. Alright? Always check my calculations. And that will be 2.2 times 10 to the 4 Newton per coulomb. Now tell me, what is the direction of that electric field? The direction of the electric field, this is a positive charge. You see, the electric field due to a positive charge will be directed away from it. So the electric field here, due to that positive charge, will be directed away from it. There you are. This will be E1, which is 2.2 times 10 to the 4 Newton per coulomb. Similarly, what will be the field at this point due to the charge Q2? It will be the same amount, because all these quantities will be the same. Alright, the field at x equal to 4 due to Q2 will be KQ2 over R squared, where Q2 is the same, 6 nanocoulomb. Is that right? Yes. And that will be KQ2 over R squared. That has the same magnitude, 2.2 times 10 to the 4 Newton per coulomb. What is the direction of that field? Well, Q2 is also a positive charge, isn't it? Q1 equal to Q2 equal to positive 6 nanocoulomb. So the field at this point due to Q2 will be directed away from it. That is the direction of E2. Okay, we now know the magnitudes of E1 and E2. How do we find the vector sum of these two forces, of these two electric field vectors? First of all, we need to obtain the angle each one of them makes with the x-axis. If you know one angle, then you know the other. Alright, can you give me a strategy for finding this angle? Angle made by E2 with the positive x-axis. Well, that angle is the same as this angle. You see that? Vertically opposite angle. And you can find this angle. The opposite side of that angle is 3 and the adjacent side is 4. Therefore, if theta is that angle, tan theta will be 3 divided by 4. Alright, so here we have E1 and E2. The angle made by E2 with the x-axis, as I was telling you, the angle made by E2 with the x-axis, this angle is the same as its opposite angle. Is theta equal to tan inverse of 3 divided by 4, and that will be 37 degrees. So if the angle made by E2 with the x-axis is 37 degrees, what is the angle made by E1 with the positive x-axis? That will be negative 37 degrees, because the angle made by E2 is a positive angle. The angle made by E1 is a negative angle. The angle made by E1 with the x-axis is then negative 37 degrees. Can you now write each of these vectors in the x and y component form? Well, once you know the angle, this E1 will be equal to its magnitude times cos of angle theta, that is the x component, and the magnitude times sine of the angle will be the y component. So let's start with E2. E2 is 2.2 times 10 to the 4, that is the magnitude of it we calculated early, 2.24 times 10 to the 4 cos 37 degrees I, that is the x component, plus 2.2 times 10 to the 4 sine 37 degrees j, that is the y component. So E2 has this x component and this y component. And now use your calculator to find the value of that. That will be 1.76 times 10 to the 4i, that is the x component, and 1.3 times 10 to the 4 is the y component. There you got the x component, 1.76 times 10 to the 4, and the y component is 1.3 times 10 to the 4. So we have taken care of E2 as its x component and y component. Let's do the same with E1. Can you write E1 the same way? The only difference is the angle is now negative 37 degrees. So E1 equal to 2.2 times 10 to the 4 cosine of negative 37 degrees I, that is the x component, plus 2.2 times 10 to the 4 sine negative 37 degrees j, that is the y component. And that will be 1.76 times 10 to the 4i, that is the x component, there you are, minus 1.3 times 10 to the 4j. Look at the y component is negative. And what do you notice here? The y components of the two are equal and opposite, they cancel. So when you want to add E1 to E2, the y components, the positive and negative, they will cancel, and the x components will add up. So E1 plus E2 equal to 1.76 times 10 to the 4i plus 1.76 times 10 to the 4i, that will be 2 times 1.76 times 10 to the 4i, that will be 3.52 times 10 to the 4i. That is the resultant electric field at that point. Alright? Okay, that is the first part. What is the second part? We now know that the electric field at this point is 3.52 times 10 to the 4i. What is the force exerted on a third charge Q0 equal to 2 nanocoulomb when you place it there? If you remember electric field, what is the definition of electric field? Electric field is the force per unit charge. Therefore, what will be the force on this charge when it is placed in that electric field? Force will be electric field multiplied by the charge. Force on Q0 equal to 2 nanocoulomb placed at x equal to 4 will be F equal to Q0 times E. I hope that concept is now very clear. When you place a charge in a field, it will experience a force given by F equal to Q0 times E. And now Q0 is 2 nanocoulombs, 2 times 10 to the 9 coulombs, and the electric field is 3.52 times 10 to the 4i. Now you must keep that direction. This is an x vector, so the force also will be an x force. That will be 7 times 10 to the negative 5 Newton I. You must specify that direction because this is a vector. So that will be that vector. Okay, let's now move on to do another one. Alright, I want you to do a quick check. Charge Q acts as a point charge to create an electric field. Its strength measured at a distance of 30 centimeter is 40 Newton per coulomb. What is the electric field strength at a distance of 90 centimeter from the charge? Well, I have a charge Q placed at a point, and I measured the electric field due to that charge 30 centimeters away from it, and I got the field as 40 Newton per coulomb. Now the question is, use that information to find the electric field at a distance 90 centimeters away from it. Tell me, will the field at this 90 centimeter be greater or smaller than the field at 30 centimeter away from the charge? Well, the field at that point will be much weaker. Well, let's see how we can do that. If E1 is the field at 30 centimeter away from this charge, can you write an equation for E1? E1 is the electric field at a distance 30 centimeter away from a charge Q. Electric field at a point is KQ divided by R squared. So E1 is KQ divided by R. R is 30 centimeter, 0.3 squared. So I have E1 equal to KQ divided by 0.3 squared. Alright, if E2 is the electric field at 90 centimeters away, can you write an equation for E2? Well, you can. E2 equal to KQ divided by 0.9 squared. Well, what are we supposed to find? We know E1, we need to find E2. Well, you can do it in many ways. You can solve for KQ from there. KQ is E1 times 0.3 squared, and put it here in place of this KQ and calculate that E2. That is one way. Another way I'm going to show you is, because I want you to practice this mathematical manipulation. Another way is divide this equation by this equation. E2 divided by E1. You see that? E2 divided by E1 is this quantity divided by this quantity. You know, when you divide by a fraction, you reverse and multiply. Is that right? That's what I've done here. Look at this. E2 divided by E1 is KQ divided by 0.9 squared. And instead of now dividing by this, I'm going to multiply with its reciprocal. Multiply 0.3 squared divided by KQ. Do you understand that? E2 divided by E1 is this quantity divided by this quantity. And division by a fraction is the same as multiplication by its reciprocal. That's what this is. What's the advantage? You can see now KQ and KQ will cancel. So E2 over E1 is 0.3 squared divided by 0.9 squared. And that is 0.11. If E2 divided by E1 is 0.11, what is E2 equal to? E2 is E1 multiplied by 0.11. There you are. And you know E1. E1 is 40 Newton per coulomb. So that will be 0.11 times 40 Newton per coulomb. And that is 4.4 Newton per coulomb. A very important concept. Okay, let's do another problem. We will now look at motion of point charges in electric field. You see, you know that if you place a charge in an electric field, it will experience a force and therefore it will move. Just like you place the basketball in the gravitational field, it will experience a force and will move. Alright, let's talk about that now. Since a point charge placed in an electric field experiences a force, it will accelerate and hence move. Tell me, if a charge Q is placed in an electric field E, what is the force experienced by that charge? We talked about it several times already today. If a charge Q is placed in an electric field E, the force the charge will experience will be F equal to Q times E. When a charge Q is placed in a field E, the force it will experience is F equal to Q times E. Now, but the net force on an object will produce an acceleration. Newton's second law of motion tells us that F must be equal to ma. That means this Q times E must be equal to mass times acceleration. So I can say, I can solve from here, if F equal to ma, then A equal to F over m, there you are, and replace this F by Q times E. Now we'll get acceleration of a charged object of mass m carrying a charge Q coulombs in an electric field E. If you replace this F by Q times E, you get A equal to QE divided by m, and I'm going to write it as Q over m multiplied by E. A very important relation. When an electric charge Q that has a mass m is placed in an electric field E, it will experience an acceleration, and the acceleration is given by Q over m times E. Okay, a positive charge will experience a force in the direction of the field, and a negative charge will experience a force opposite to the direction of the field. Well, that must be very clear by now. Let's do a small problem. An electron has an initial velocity of 2 times 10 to the 6 meter per second in the x direction. It enters a uniform electric field E equal to 400 Newton per coulomb J, which is in the positive y direction. A. Find the acceleration of the electron. How long does it take the electron to travel 10 centimeters in the x direction in that field? By how much and in what direction is the electron deflected after traveling 10 centimeters in the x direction? Well, you know, can we think about it for a while? We have an electric field directed upward. Tell me, if you place a negative charge in that electric field, will the negative charge experience an upward force or a downward force? Well, a positive charge will experience a force in the direction of the field. A negative charge will experience a force opposite to the direction of the field. That means if you have a field that is directed upward and a negative charge comes into that field, it will experience a force opposite to that. Right? Now tell me, if I have a basketball here, if I throw it horizontally, what kind of motion will it have? If I throw it horizontally, it is going to go in a parabola like this. Is that right? There you are. So the basketball, if I throw a basketball in a gravitational field, this is going to go like this. Now the same thing is going to happen to the electron. Look at this. This is the electric field which is directed upward. So the poor electron comes up here, all of a sudden it gets caught inside the electric field. The electron will experience a force which way? Opposite to the direction of the field, downward. That means that electron is going to go exactly like our basketball. Why? Because the basketball experiences a force downward. the electron will also experience a force downward as it moves. So the electron is going to move like this. When it enters here, it will go like this. That means it will travel a horizontal distance x and a vertical distance y. Now, we have actually talked about these kind of motions when we did projectile motion. Well, we are going to use those concepts in here. Okay, let's put these things down. Well, this is the motion of the electron that we have been talking about. The initial velocity of the electron is in the x direction. You see, before it enters the electric field, the electron had an x velocity. It has no velocity in the y direction before entering the field. So we can say Vx0. What does Vx0 stands for? The x velocity before entering the field, or at the instant when it entered the field, is 2 times 10 to the 6th meter per second. That is given to us. Tell me, what happens to this x velocity as the electron enters the field? Let me see how many of you remembers the concept in projectile motion. You see, this electric field will not affect this x velocity. The electric field will only affect the y velocity. You see that? The x velocity will not be affected by the electric field. That means this Vx0, that is 2 times 10 to the 6th meter per second, will remain a constant as the electron moves through the electric field, because there is no force in the x direction. Vy0, initial y velocity is 0. And as the electron travels, its y velocity is going to increase. Just like the basketball falling, the electron will fall. Its y velocity will increase. Let's talk about it. Since the field is in the positive y direction, let's start with part A, then we will come back to the part C later. Part A, find the acceleration of the electron. Well, since the field is in the positive y direction, the force experienced by the electron is in the negative y direction. The acceleration in the y direction therefore is, alright, what is the formula for the acceleration we derived? A equal to q over m times e. A equal to q over m times e. What is the charge carried by an electron? 1.602 times 10 to the negative 19 coulomb. What is the mass of an electron? Can I remember it? Is it 9.1 times 10 to the negative 31 kilograms? Approximately, yes. The charge on the electron is 1.60 times 10 to the negative 19 coulomb. Mass of the electron is 9.109 times 10 to the negative 31 kilogram, times E is given to be 400 Newton per coulomb. And that gives me the acceleration of the electron. Look at this, it's a tremendous value. 7.03 times 10 to the 13 meter per second squared. Now, you must understand, I haven't given you the direction here. This must be negative j because it is directed downwards. This acceleration is in the negative y direction. So this is just the magnitude. You must understand that it is directed in the negative y direction. So the acceleration must be understood like this. Negative 7.03 times 10 to the 13 meter per second squared j. That is the acceleration of the electron. And now, with that acceleration, the electron is falling. But before that, we must say the x velocity. The electron has an x velocity which does not change. The electron is going to travel in the x direction with that uniform velocity. That means if t is the time taken by the electron to travel 0.1 meter from, if suppose this is the origin, x equal to 0 to x equal to 0.1. The electron is going to travel like this. That means it travels the distance x equal to 0.1 in a time t, alright, and it has a constant velocity of 2 times 10 to the 6th meter per second. Can you find that t? Let me repeat that again. The electron moves with a horizontal x velocity of 2 times 10 to the 6th meter per second, and it travels a distance of 0.1 meter. What is the time taken for that? Well, that time will be t equal to x divided by the velocity. Is that right? X is 0.1 meter. The velocity is 2 times 10 to the 6th meter per second, and therefore that time is 5 times 10 to the negative 8 seconds, which is about 50 nanoseconds. So the time taken by the electron to cover a horizontal distance of 0.1 meter is 5 times 10 to the negative 8 seconds. During that time, the electron is falling vertically. We need to find that vertical fall. What is the vertical fall of the electron? Okay, so the acceleration of the electron, the downward acceleration of the electron is negative 7.03 times 10 to the 13 meter per second squared J, and the time taken for the electron to travel, the electron has been traveling for this many seconds. That means it has been accelerating at this rate for this much a time. Now, can you give me an equation to find that vertical distance traveled by the electron? Y equal to v by 0t plus 1/2 a t squared. Have you forgotten that equation? Where v by 0 is the initial y velocity, which is 0. Therefore, y, the distance traveled by the electron during that time, will be 1/2 a t squared, where a is this value and t is this value. So let's put that in there, and that gives me 1/2 a times t squared. That is negative 0.088 meter. The electron will be deflected from its original path by a distance of negative 0.088 meter. Now, let me tell you, this is the most beautiful problem you will see in this part of the course. So try this one more time and try and understand how to do these kind of problems. Okay, let's do another one. A mass of 2 grams located in a region of uniform electric field 300 Newton per coulomb I carries a charge Q. The mass released from rest at x equal to 0 has a kinetic energy of 0.12 joules at x equal to 5 meter. Determine the charge Q. Okay, well, we have the mass of the object is 2 times 10 to the negative 3 kilogram, that is 2 grams. Its kinetic energy, well, let me see if I can draw that for you. We have an object that carries a charge Q released in an electric field. Look at that, this is the electric field, and this is the object that carries a charge Q. And assuming that the charge is a positive charge, it's going to experience a force in the forward direction, in the direction of the electric field. That means as it moves, it is going to acquire speed, and that is why it has kinetic energy. Now, when it moved through a distance of 0.5 meter, it acquired a kinetic energy of 0.12 joules. Okay. We have kinetic energy is 1/2 mv squared, so we can find the velocity. Now, therefore, what is v equal to? V squared equal to 2k divided by m. We know the kinetic energy, we know the mass. Using those values, I get v squared is 120 meter per second squared. And we will now carry the value of v squared. Now tell me, if you know the value of v squared, can you find the acceleration of the object? Well, when the electron came out here, when the object is here outside the field, its velocity is 0. Now, after it traveled a distance x equal to 0.5 meter, the v squared here is 120. Alright, we know the distance it traveled, and you know the initial velocity, you know the square of the final velocity. Is there a relation connecting initial velocity, final velocity, displacement, and acceleration? Yes, we have. We now find the acceleration using the relation v squared equal to v0 squared plus 2ax. That's the relation. v0 is 0. Therefore, 120, v squared is 120, equal to 2a times x is 0.5, and I can now calculate the acceleration. Therefore, a equal to 120 meter per second squared. You see how we started with kinetic energy, from there we calculated v squared, and then we used that to calculate the acceleration. Now, if you know the acceleration, we can now find whatever we are looking for. What are we looking for? Well, we're looking for that charge q. We know A equal to Q over M times E, or Q equal to A times M divided by E, and we have all these values. A is 120 meter per second squared, and mass is 2 grams, 2 times 10 to the negative 3 kilogram, and E, the electric field, is given to us is 300 Newton per coulomb. Therefore, Q equal to 8 times 10 to the negative 4 coulombs. That is 800, no, not nanocoulomb, it has to be microcoulomb, because this is 10 to the negative 4. That will be 800 microcoulomb. That's right. That will be micro. Okay. Well, I think that should be enough. We have done a number of problems in calculating electric field intensity and force experienced by a charge in an electric field, and calculating the acceleration and so on. Well, we are going to use all these concepts in our next lesson, so you cannot forget these. Alright, review the homework. Now remember, the more you understand the earlier lesson, the better will be for you to understand the lessons that is to come. Alright, so I hope you will come prepared for the next lesson. I will see you for the next lesson a little later.